At the beginning of 2010, when you guys were all like, what, 6 years old, 5, 6, 7. What? What did you say?
I said 6. I was
You-
6 years old.
Are you back from your trip to outer space? Okay, perfect. All right, so we've got this differential equation, dw dt is 1/25 of w minus 300. We wanted to make a tangent line. So the tangent line should be easy. We need a point and we need a slope. Right? Same thing we always need, right? So our point should be 0, 1400, because that's the initial condition that they gave us. And our slope should be the value of dw dt at 0, 1400. And that ought to be 1100 over 25, which must be 44. Does that sound right? Yeah. Is that right, Philip? Yeah. Okay. You just looked unhappy about that 44. You good with 44? Okay. All right. So our equation ought to be y equals 44t plus 1400. I just put it in slope intercept form because they gave us a y-intercept, but if you wrote it in point slope form, that's fine also. And then we were supposed to approximate that when t equals 1/4. So at t equals 1/4, that ought to be 1411. Good or no? Everyone's good? Anybody in the Zoom have a question on that one? Y'all are good? Okay.
Yep.
Part B, find the second derivative and determine if our approximation was under or overestimate. So finding the second derivative, let's do it on a new page. Part B, our second derivative, we know that we're going to have to, what was it, 1/25th, right? It was 1/25th times w minus 300. So the 1/25th just stays out there, and then the w minus 300 differentiates to become dw dt, which when we replace the dw dt with the original dw dt, we end up with this. That sound good, everybody? And then we would determine that for all of our values, right? We know that w is always greater than 1400. How do we know it's always greater than 1400? We started at 1400, and it says in the initial problem that the function is always increasing. So we know w is greater than 1400, which means that the second derivative is greater than 0, which means that it is concave up. And if a function is concave up, the tangent line will be an underestimate. Everybody good there with that? And make sure you write that out. A tangent line is an underestimate because the function is concave up. And give a reason why the function is concave up. Right? You need to say that it's concave up because the second derivative is positive for all w values greater than 1400, which is what we've got. Zoom, questions?
Do you have to write like it's greater than, or the second derivative is less than 0, like as a sentence, or can you just write the less than symbol?
You can just write the symbol, but that's a greater than symbol, not a less than symbol.
Oh wait, but, oops. Yeah, never mind.
Yeah. But yes, writing the symbol is fine. If you wrote what I wrote, you would be good.
Okay, thanks.
Yep. All right, part C. What did part C ask us to do here? To solve the differential equation. So we've got dw dt is 1/25 of w minus 300. And we'll separate the variables. The reason we separate them is because the dw up here matches up with this w minus 300. So we got dw over w minus 300 equals 1/25 dt. Everybody good with that? Integrating the right gives you 1/25 t plus a constant. Integrating the left, you do the u substitution, u equals w minus 300, and you get du over u. and you end up with natural log absolute value of W minus 300. Everybody good there? Yeah? Yeah. Okay, cool. Then we will exponentiate. Actually, then we will solve for a constant. Sorry, solving for a constant, we need to plug in our initial condition. So that's W is 1400, which 1400 minus 300 is 1100. Initial condition was 1400, right? Yeah, okay. I can subtract. Don't worry. And then that gives us 0 plus our constant over here. Everybody good? So now we have natural log absolute value W minus 300 equals 1/25th t plus the natural log of 1100. I mean, I got rid of it because the value is 1100. So the absolute value of 1100 is just 1100. Good? Yeah. I mean, if you keep it there, that's fine. It doesn't matter. All right, then we'll exponentiate, which will give us an absolute value of W minus 300 equals 1100 e to the 1/25th t. We can bring the ln of 1100 out in the front as a coefficient. And then the absolute value will just end up disappearing, because if we get rid of it, we can get either the positive or the negative, but we need the positive there, because when t is 0, that makes the right-hand side 1100. And the left-hand side, when W is 1400, should be 1100. And so we need them both to be positive. So we'll just say W minus 300 equals 1100 e to the 1/25th t, or W equals 300 plus 1100 e to the 1/25th t. Good or no? We're feeling okay about these differential equations, and are these real world ones? Yeah, hopefully. Okay. Oh yeah, question.
Could you repeat like how you determine whether to use the positive or negative version of the absolute value?
Yeah, you just use your initial condition. So if you plug in 0 for t, right, your initial condition was 0, 1400. True?
Yeah.
You just plug in 1400 for W, which gives you 1100 on the left. And you plug in 0 over here, which gives you either a positive or a negative 1100 e to the 0, which is just positive or negative 1100. And since we need a positive 1100 from what we have over here, we keep the positive. If we had a negative 1100 over here, then we choose the negative.
Oh, okay, got it. Thanks.
Any other questions? All right, how were the fish? They were what? Okay. Did you all do okay with the fish at least? No? Didn't do okay with the fish? What? You are a teenager. Teenagers often have questionable methods on everything. What? Somebody in the Zoom saying something?
I could do A and B.
That's great. That's better than not being able to do A and B. All right. Let's see if we can do A. A should be really easy. A should have been the easiest part. All right. How many fish enter the lake? Well, the number of fish that enter the lake is the integral of the rate at which they enter the lake, right? That's what I was saying before we left, is if you need to figure out how much of something, integrate the rate function. So all we got to do is integrate from 0 to 5 e of t dt. And that equals, what does that equal?
I got 153.
When we go to the nearest whole number, 153 fish. Easy enough? Everyone good with that? Okay. Part B, the average number of fish that leave the lake per hour over the 5-hour period. Well, that's just the mean value theorem, right? We're looking for the average value, so that's the mean value theorem for integrals. 1 over b minus a times the integral from a to b of L of t dt. which came out to be what? Guess I could pull up the scoring guidelines so I could tell you how many points things are worth too.
6.059 fish per hour, I think.
6.059 fish per hour. Everybody good with that? Yeah. The integrating part just gives us the number of fish that leave, and then dividing it by the 5 gives you the. All right, everybody's okay with A and B? Let's see here. Let me see how many points each of those were worth. The first one was worth 2 points. Yeah, they're both worth 2 points. One for the integral and one for the answer. One for the integral, one for the answer. Everybody good with that? Yeah. All right, part C. This is where things start to get slightly more difficult. At what time is the greatest number of fish in the lake between 0 and 8, inclusive of the endpoints? Justify your answer. So, the number of fish in the lake. What is a function to represent that? Not quite. That would be the rate of change of the fish in the lake, because E and L are both rates, right? So the number of fish in the lake is the integral from 0 to t of E minus L. That should be the number of fish in the lake. The integral from 0 to whatever t value we want of the amount that enter, minus the integral from 0 to t, whatever t value we want of the rate at which they're leaving. Right? So integrate the rate they enter, integrate the rate they leave, and that tells you how many entered and how many left, which will tell you how many are in the lake. Does that make sense? All right. Everybody at home good with that? Zoom good?
Good.
Good.
Good, Zoom. Okay. So we want to find when is that at a maximum, I think is what it is. Maximum, not minimum, maximum. Okay. So a maximum can only occur at an endpoint or a critical value. So we need to find the critical values of this function. Well, the critical values come from its derivative, right? So we're taking the derivative of the integral from 0 to t of E minus L. Everybody good with that conceptually? What is the derivative of the integral of a function from a constant to a variable? It's just that function, E of t minus L of t. So we want to know, when does E of t minus L of t equal 0? Or effectively, when does E of t equal L of t? Either one. And luckily, you have a graphing calculator for this problem. So you would just graph E minus L, see when it has an x-intercept. Or you graph E and you graph L and see where they intersect. And it came out to be a t value of 6.204. Everybody good with that? Then we need to determine, because it says the greatest number of fish in the lake, we need to determine if that's a maximum or a minimum. Because if that's a maximum, then great, we're done. But if that's a minimum, then we got to also look at the endpoints, right? So we can do a sine chart with our derivative. This is E minus L. And so you could just plug some value greater than 6 into E minus L and see what you get. And you end up getting a negative. And if you plug in some number less than 6, like or less than 6.2, like 6 or 5 or 1 or whatever, you end up getting a positive value. So that should show you that you have a max span. Okay? And you would need to show that E of 5, let's say, minus L of 5 is greater than 0. And then we'll say E of 7 minus L of 7 is less than 0. You need to show that that's true by plugging in a value and giving the value from your calculator. Show that those, to the right it's positive and to the left it's negative. that make sense, everyone? Now, they did not ask how many fish are in the lake, but sometimes they do ask things like, oh, how many fish are in the lake at that maximum? In which case, you would need to plug in 6.204 into this integral, right? And that's another way that you could have justified that the max was at 6.204. You could have made yourself a little chart with t-values of 0, 6.204, and 8, the two endpoints, right? And then you could have found the number of fish. At 0, you would have found that there were 0 fish in the lake, right? Because the integral from 0 to 0 of a function is 0. At 8, you would have got some value. You would have got 80.91998. And at 6.204, you got 135.01492. And you would have said the max number of fish in the lake occurs at t equals 6.204. So a sine chart or just a chart showing the values, either one is good. Yeah. Yeah, so you're good with there being an integral to represent the number of fish in the lake. Yeah, so we want to know when is the number of fish in the lake at a max. So in order to find the max, we have to take the derivative. So that's why we took the derivative. And then the derivative and the integral cancel because it's the derivative of an integral. That good? Yeah. Everybody at home good?
Yes.
Yep.
Great. Okay. Was that the last part of that one? No, there was a part D, wasn't there? Oh, and you probably want to know what the point breakdown for that was. Let's see here. 1 point for setting E minus L equal to 0, 1 point for 6.204, and 1 point for justification, whether it was a chart with values or a sine chart with some stuff attached to the side of it to prove how you got those values. Good? Okay. Part D, let's see, part D said, is the rate of change in the number of fish in the lake increasing or decreasing at 5? Well, what represents the rate of change of fish in the lake? What? The second derivative of what? You did the second derivative of this? Yeah, that's correct. Right, the rate of change ought to be the rate they enter minus the rate that they leave, right? And so if we want to find out if this function, the rate that they enter minus the rate that they leave, is increasing or decreasing, we need to take its derivative, which is effectively the second derivative of the formula we wrote in part C. We want to know if that's what's going on with that at 5. So we just do E prime of 5 minus L prime of 5 and figure out what that value is. Your calculator will take the derivative for you at the point. You don't need to find the derivative and evaluate it at 5. You just need to have your calculator evaluate the derivative of each of those functions at 5. And that value comes out to be negative 10.7228. And you would say that's less than 0. Therefore, the rate of change is decreasing. Good or not? That's it. Yep. Yep. I mean, their work, yeah, literally all they even wrote on their scoring guidelines is basically this. They wrote E prime of 5 minus L prime of 5 equals negative 10.7228, which is less than 0. And then they wrote, because E prime minus L prime is less than 0, the rate of change in the number of fish is decreasing at t equals 1. Good. Any questions on that? Feel like it's not as bad now that you've seen it? Yeah. Maybe it makes the escalator one a little easier. The escalator one still sucks. You haven't looked at it though since finishing the last one. correctly and feeling confident. Maybe it doesn't suck. I don't know. Should we just go straight through it? Or do you guys want to take a second to see if you can fix up anything that you might be able to do better now? All right, I guess we'll just go through it since there's no response. Okay, cool. So we have a function for people entering the line for an escalator. And then we have another, well, we have a rate at which they're leaving the line for the escalator, 0.7 people per second. And we're given an initial value. There are 20 people in the line at t equals 0. Okay. We want to know how many people enter from 0 to 300 seconds. Should be just as easy as the last one, integral 0 to 300 of r of t dt. And what did that come out to be? 270. Everybody good with that? Now it says during the time interval 0 to 300, there are always people in line. How many people are in line at t equals 300? Well, let's see. We started with 20 people in line. And during the time period from 0 to 300, 270 people joined the line. But 0.7 people left every second. So how many people left? 0.7 times 300. So 290 minus 210, that looks like. I wrote 2. That ought to be 80. Not even really any calculus for that one, huh? Any questions on part B? All right, we want to know at what time are there no people in line for the first time after t equals 300? Well, we know that at t equals 300, there were 80 people. So how long does it take those 80 people to get in the line? Well, take 80 people and divide it by 0.7 seconds per person. And what does that come out to be? 114 point what? 2857. Is this the correct t value though? No, because we're talking about after 300. It's 114 seconds after 300 seconds. So we should say add the 300 to that. Gives us 414.286 if we round seconds. Good or no? Feeling better about the escalator problem already? Yeah, not bad. You still don't like part D? All right, part D. At what time is the number of people in the line a minimum? Okay, well, how many people are in the line at any given time? 20 to start with, plus the integral from 0 to 300, but 0 to any t value of r minus how many people leave? 0.7 every second, right? Minus 0.7 t. That's how many people are in the line at any given time. Everybody agree with that? Okay, we want to know when is this function. So what do we call this? We'll just call this p equals this number of people in the line. We want to know when that's at a minimum. So find the derivative. P prime is, well, let's see, the derivative of 20 is 0.
Oh,
The derivative of the integral from 0 to t of r is just r. So P prime is r of t minus the derivative of 0.7 t, which is
0.7.
0.7. Everybody good there? Okay. Yeah. So then we want to see when is that equal to 0? So you can either graph r of t minus 0.7 and find the x-intercept, or you can graph r of t and you can graph y equals 0.7 and see where they intersect. Let's see. Anybody got the values for that? I don't have the scoring data for this one. I can pull it up. But I believe there was 2 of them.
33.013 and then 166.575.
T equals 33.013298. And T equals 166.574719. And those just come straight from using your calculator to approximate the intersection of R of T and 0.7 or the x-intercept of R of T minus 0.7. Now, in this case, a sine chart's not really going to help us out, because if I try to put both of these on a sine chart with my endpoints, I'm either going to find that it does this, right? And my minimum could either be at 0 or at 166, or I'm going to find that it does this, and that my minimum is either at 33 or at 300. So really what we need to do is just figure out the value of the number of people in the line at each of these 3 places. And if we can figure out the value of the number of people in line at each of these, 4 places, then we should be good. So here's T values, here is values of P, 0, 33 point whatever, 166 point whatever, and 300. The value at 0 we know, right? How many people were in line at 0? 20, right? 20 plus the integral from 0 to 0, which is 0, minus 0.7 times 0, which is 0. So 20 plus 0 minus 0. What about at 300? We already found that also, right? What was that? Was it 270?
Wasn't it 80 people?
I thought it was 80. I don't know, I can't remember. I think it was 80 because we subtracted the number to the left. Yeah. So clearly, this is not going to be the minimum because there was less people at the start. Then we just need to evaluate this function at 33 point whatever and 166 point whatever. So just evaluate the integral from 0 to 33 of r minus 0.7 times 33 whatever, and then add 20 to it, and you get 3.803. And when you do it for 166, you get 158.070. And so we should be able to then see that because the only place where we could be at a min or a max is at a critical value or at an endpoint, the lowest of the critical values and endpoints is 3.803. So that's the least number of people ever in the line. It happens at T equals 33.013298. And that was worth 4 points for that one. 1 for setting this equal to 0, 1 for identifying 33 as a potential value, 1 for the answers, and 1 for your justification, which is the full chart. Does that make sense, everyone? Everyone did that? Did? Okay. Making sure. Okay. Well, I wasn't sure. There was some sort of something. I didn't know what it was. All right, we're all good. Anybody have any questions on that? Okay. That's the last one I asked you guys to do, right? Yeah. Okay. Let's briefly talk about another area volume one. Yeah. Do I have that open? Oh, I don't have that open. Okay. While I'm opening up the other area volume stuff, let's there we go. Let's talk about what I want you guys to do for tomorrow. So for tomorrow, we're going to talk about an area volume one in a second as soon as that loads. Tomorrow, I want you guys to do the next rate problem, which is about bananas. Bananas. Yeah, bananas. A banana's on a display table in a store. Very exciting. You're going to do the banana problem for tomorrow. And then additionally, you are going to open up the document that is called graph FRQs. and try to do the first two of those. Nobody ever likes the graph FRQs. Okay? If you didn't like the rate FRQs, you're gonna dislike the graph ones even more, I bet. Yeah. I think they're probably the most difficult to begin to grasp. But once you get them, they're fine, just like all the rest. So you're gonna do bananas and graphs 1 and 2 for tomorrow. Everybody good on that? Everybody clear with that? Yeah. And if this area and volume FRQ document will ever open up, we'll do one of those. Doesn't seem like it's opening. If you get bored and want to do the next rate question about water, you could do that one. If you see, if we go through all the rate questions, most recently they got a little interesting. There was fish, there was escalators, and then there was bananas. And then you keep going. This one was about water. This one is about rainwater. This one, oh, this is a good one. This one was about unprocessed gravel. Ooh. This one is again about rainwater, but it's really cool because it's rainwater in the town of Stormville, and also rainwater on Monsoon Mountain. Ooh. And then this one, oh, this one's also about water. And then this one's about a swimming pool, so that's water. This one's about snow, so that's water. This one's about trees, they need water. This one's about a storm washing away sand on a beach, that's water. And, oh, this one's about a rock concert, that's exciting. There's all kinds of fun rate questions. Yeah, you need water at a rock concert, otherwise you'll get dehydrated, right? You don't want to get dehydrated. That'd be bad. At some point, the document with the area and volume FRQs will open, and then we can do that. We won't have to just sit here and talk about these. Let's see. While we're waiting on that, why not? We've got the differential equation ones open, right? We could look and see what they're about. Look, that one's about a slope field. Look, that one doesn't have a slope field. Look, that one's about a tree. Another problem about a tree. That one's a slope field, and another slope field, and another slope field, and another slope field, and another slope field. Oh, another slope field. Slope field. Coffee pot. Could be a coffee pot. It says it's a coffee pot with the shape of a cylinder. I mean, I don't know. Coffee's gross anyway. Why would you want coffee? Look at all these fun problems. So many fun problems. How come the area? Making the it loaded. That's exciting. All right. So we already talked about the first two of these, I believe, earlier. Does that sound right? We did the first two. Okay. I did the third one during whatever the last class period was, but I want to do another. I'm going to do a non-calculator one. Which non-calculator one do I want to do? I think I want to do this one. This is one I asked you guys to do. Number 5. Yep. Does that look right? You guys did this one? Zoom people, did you do this problem?
Yes.
Wonderful. You guys good? Yeah, you guys did do this one? Yeah, the people here, yeah, you got it? Okay. All right. First off, find the area of R. Great. So in order to find the area of R, the first thing we need to do is we need to figure out which function is above the other function, right? So which one of these is above the other one? Which one is the upper function?
G of x.
Yeah, g of x is above f of x, right? We should be able to tell that because f of x is a quadratic, it's a parabola, and it has a value that is positive, so it must open up, right? So that'd be the concave up one on the bottom. All right, so the area of R ought to just be the integral from 0 to 2 of g of x minus f of x. Everybody good with that? Okay. So make sure you distribute the minus sign for everything. How do we integrate 4 cosine 1/4 pi x? We got to do a u substitution. where u is equal to 1/4 pi x. We're trying to integrate 4 cosine 1/4 pi x. We're going to let u equal pi x over 4. And du will be pi over 4. Yeah? Everybody good with that? So I'm going to have to put in a pi over 4. Which means I'm going to put in a 4 over pi out here. And the pi over 4 will go with my dx to become a du. So we'll end up with cosine u du. But then I have this 4 plus this 4 over pi, which is going to give me a 16 over pi out here. Everybody good with that? Yeah? Okay. So we've got the integral from 0 to 2. Actually, we'll just integrate it right off the bat here. So the integral of this is sine u. So we have 16 over pi times the sine of u, and u was pi x over 4. Then the integral of minus 2x squared ought to be minus 2/3 x cubed. And the integral of a positive 6x ought to be a positive 3x squared. And the integral of a minus 4 ought to be a minus 4x. And now we will evaluate from 0 to 2. And if I plug in 2, this is 16 over pi times the sine of pi over 2. What's the sine of pi over 2? 1. So 16 over pi minus 16/3 plus 12 minus 8. Everybody agree with my arithmetic there? Okay. Minus, if I plug in 0, what's the sine of 0? 0, right? And what's 0 cubed? 0, and 0 squared? 0, and 0 times 4? 0, so minus a bunch of 0. So there's your answer. 16 over pi minus 16/3 plus 12 minus 8. That's 16 over pi. And then this is a plus 4. So that'll be minus 4/3. Good or no? A little bit messy. Got to deal with that first integral with a u sub, but it could be worse. Yeah. What about part B? Part B asks us to write, but we don't have to evaluate, an integral expression to give the volume if we take r and rotate it around y equals 4. So if I'm going to rotate around y equals 4, my outer radius is the lower function, and my inner radius is my upper function. Everybody agree with that? It comes from that. So my outer radius is 4 minus, what is this? 4 minus f of x, right? And my inner radius ought to be 4 minus g of x. So for part B, our equation should be pi times the integral from 0 to 2 of 4 minus f of x squared minus 4 minus g of x squared. Yeah. Good or no? Feel okay about that? Okay. What about part C? Now that region is the base of a solid. The cross sections perpendicular to the x-axis are squares. So I've got this thing here. Cross sections are squares. The area of the square is the side length squared. What is the length of the side? It is the upper function, which was that f of x or g of x? Now I don't have it in front of me. G of x minus the lower function, which was f of x. So we should integrate from 0 to 2, g of x minus f of x squared, or side length squared, dx. And I think it said you didn't need to evaluate that one either, right? Pretty straightforward. As long as they have defined it as f of x and g of x, you are welcome to just continue using that throughout. You you don't need to rewrite. In fact, I would recommend using that, because when you go back through and you accidentally write 2x squared plus 6x plus 4 instead of minus 6x, then you end up losing 2 points on that problem because you didn't have your integrand set up correctly. All right, cool. I think that's going to be all that we go through today. We have 15 minutes-ish left. Maybe we work on the banana problem. You guys want to try and work on the banana problem? Yeah, that'd be good. All right, let's work on the banana problem. Till class is over, you can work on the banana problem. Yeah, independent. But Zoom people, you still have to work on it. You have to work on the banana problem.